Hello everyone, this is Nash. Today we would like to talk about the RL circuit. In my previous video, we talked about the RC circuit. The R means the resistor and the C means capacitor. And today I would like to replace the capacitor simply by the inductor, denoted by a capital letter L. So first, what is inductor? Inductor is basically conducting wire, but in the shape of a coil and wounded sometimes around a core material, and sometimes you don't need the core material, but at least you should wound it in series of loops. So due to the nature of the coil of wires, it will always like to oppose the change of the magnetic flux. And however, the magnetic flux is built by the current, so opposing the change of the magnetic flux corresponds to opposing the change of the flow of current. So let's say if you now close the switch and you start to charge your inductor, and what will happen? Can your current immediately reach its maximum value? Today, we would like to talk about the RL circuit. First, let me remind you, what is resistor? How do we define the resistance? And the resistance is the potential difference across your resistor divided by the current passing through it. So we can simply derive that the potential difference across your resistor is equal to I times R. So your resistor always like to oppose the current directly. So that is why the voltage is always proportional to the current. So let's look at the inductor. How do we define the inductance? The inductance L is the total magnetic flux, which is the number of the loops and times the magnetic flux for each loop and divided by the current passing through it. So this is how we define the inductance. Okay, so let me remind you, if you want to calculate the secondary EMF induced by your inductor, which is against the voltage supply, and it can be written as the V sub L means the secondary EMF, which is minus dm times phi b divided by time. Okay, and since the n phi b is equal to I times L, so keep going, it could be equal to minus inductance and times di by dt. The di by dt means the rate of change of the current with respect to time. So this is the difference between the resistor and inductor. The resistor would like to oppose the current directly, but for your inductor, it would like to oppose the change of current, the rate of change of the current with respect to time. So maybe in my next video, I would introduce you what if we replace the DC generator simply by the AC generator as our voltage source, and the current of the inductor is going to lag behind the voltage by 90 degrees. Interesting. But today in this video, I would like to show what will happen if the R and L is now attached by a DC generator. Okay, let's keep going. So we now got the potential difference across the resistor and potential difference across your inductor. Then that means we are ready to use the Kirchhoff's law. Okay. Okay, some of you might be wondering, hey Nash, what does it mean for the minus? Actually, the minus, you can even ignore that. The reason why I write it down right here, the minus means your inductor is going to induce the secondary EMF, which is against the voltage supply. Okay, and the V sub L means the secondary EMF, electromotive force. Okay, to be more specific. So what is Kirchhoff's law? The Kirchhoff's law tells us that the potential difference across the terminals of the battery is equal to the sum of all the potential differences from each component. And now we get two components. One is your resistor and the other is your inductor. So the epsilon, the voltage across your battery, is equal to VR and plus VL. And VR, according to those results we've just got, is equal to IR and plus, okay, here's the thing. You may see the minus in front of the di by dt times L, but actually what I really want to say is the size of the value is L times di by dt, and the minus means it's now against the voltage applied. But if you look at the 2 points across the inductor, this is still high potential. This is a low potential. So across the inductor, there will still be a voltage drop. There will still be a voltage drop, and the size of the drop is L times di by dt. Okay, so I can write down the VL as L times di by dt. Okay. So let's do some simple calculus, okay? First, just let me rearrange it. The di by dt. The di by dt is equal to 1 over L times epsilon minus IR. Okay, let's keep going. I can pull out the minus R to be L and minus R times I minus E over R. Okay, so let's keep going. This is I, this term contains I and this term is di. I would like to put them on the same side, to be the di divided by the I minus E over R. C is equal to minus R divided by L and times dt. So far so good. Is it okay? Now looks like we are ready to integrate all this term, the left hand side and the right hand side. We are ready to integrate it. Oh, a cleaning robot. Okay. So we can use the U substitution right here. Look at this term. You can let U, which is equal to I minus E over R. So in this way, the du is equal to di. So integrating this term corresponds to integrate the du by u, which is the natural log. So let's keep going. The natural log of I minus E over R evaluated, remember, evaluated from some initial value equals 0 to I, and integrate the dt from time equals 0 to some time t. Okay, let me close my cleaner robot. Sorry, let's keep going. Evaluated from 0 to I. Which is equal to minus R over L and times T, evaluated from 0 to some time T. Okay, here I need to remind you that the upper and downward limits is important because if you plug in 0 for I, you would get a term about the natural log of minus E over R. But if you ignore the I, you forget about the upper and downward limits, and things will be different. There will be only one term, which is the natural log of I minus E over R. But if you can consider about upper and downward limits, this will go right, because when you plug in I for I, you get a natural log of I minus E over R. You plug in 0 for I, you get a term of natural log of minus E over R. And you want them, and you want the first term to subtract the second term from the first term. So there will be a minus calculation. So let's keep going. And this term is going to be natural log. You plug in I for I, you plug in 0 for I, and turns out to be I minus E over R divided by minus E over R. Okay? On the right hand side, plug in 0 for T, that is 0, so we can ignore that. So on the right hand side is equal to minus R divided by L and times T. Okay, here's the thing. Let me remind you, the A to the log AB is equal to B. So the E to the natural log of all this term is equal to E to the minus R times T divided by L. So we can keep simplifying this, which is the I minus E over R. We can get rid of the natural log. Minus divided by minus E over R is equal to minus R divided by L and times T. E to the minus R times T divided by L. Okay, let's just rearrange it. I'm going to put this minus E over R to the right hand side, and remove the minus E over R to the right hand side, except for I. I'm going to put everything on the right hand side, and which is going to be the I as a function of time is equal to E over R and times 1 minus E to the minus T over L divided by R. Okay, check it. Is everything okay right now? Yes, it's okay right now. Okay, right here, I would like to name this digit as time constant. This is a special factor that we need to give it a special name. This is the time constant. And the symbol is tau. The tau is equal to L divided by R. In my previous video for RC circuit, we do get the same time constant, which is RC. And the RC means if I want to charge my capacitor up to 63% of the maximum value, and you should at least take a time constant for RC. And now for the RL circuit, if you want to charge your inductor up to 63%, same idea, you need to take a time constant. Okay, so how do we charge your capacitor? Actually, when you close the switch, you wish at the very beginning, you wish you can immediately reach the maximum value for your current, but however, you cannot. You cannot, since due to the nature of the coil of wire, it would like to oppose the change of the magnetic flux, and that means it would like to oppose the change of the flow of current. So when you close the switch, the current is so hard to pass through your inductor. We can check from this equation. Okay, we can discuss it. First, at time equals 0, your current I is equal to E over R and times 1 minus E to the 0. And anything to the 0 power is 1. So at time equals 0, there's no current could ever pass through your inductor. Okay, so but as time goes very, very long, let's say it goes to infinity. Let's say the time goes to infinity, and your current I will be E over R and times 1 minus E to the minus infinity. And for this term, it's gonna approach 0. So as time goes to infinity, you will reach a steady value. And the steady value is E divided by R, which is also the maximum current in the RL circuit. Okay, so we can predict as time goes by, at the very beginning, at time equals 0, your inductor is start to function. It's so strong, it would like to oppose the current for passing through it. But as time goes by, your current is going to keep increasing, and until it reaches the maximum value, which means a steady value. There's no more change for the current. So that means your inductor is going to be acting like a normal conducting wire. No function as time goes to infinity. Okay, since the maximum value for the RL circuit is E over R. It looks like as time goes by, there are only one component in your RL circuit, which is your resistor. That means your inductor will no longer function. Okay. And at time equals a time constant, which is L divided by R, and your current I is equal to E divided by R and times E minus E to the -1. And since the E over R, it's our maximum value for current, and E to the -1 is 0.37. So this is 0.63 times the I max, which means if you want to increase the current up to 63% of the maximum value, the time constant is the time at least you should take. So let me plot a diagram for you to capture the idea for the three terms. Okay. This is a diagram for your current I as a function of time. So check, at time equals 0, due to the nature of your coil of wires, there will be no current. But as time goes by, your DC, your battery is gonna keep pushing your current and try to push the current to pass through the inductor. So the current is gonna increase and asymptotically approach the value of the maximum steady value for your current. Okay, and the maximum value is E over R, which means as time goes to infinity and your inductor L will no longer function, because at that moment, there will be no change of current, no more. So your inductor will be with no function. It will start to be acting like a conducting wire. So at that time in the RL circuit, your resistor will be the only one component. So that leads to the maximum value is E over R, because your inductor will no longer function. And what is time constant? Time constant is if you want to increase your current up to 63% of the maximum value, 63% of the maximum value, this is the this is time at least you should take. But however, back to reality, can we really wait that long as time goes to infinity? Can we really wait that long if I want to increase the current up to the maximum value? No, we can't. We can't leave that long. So what is the real time? What is the time at least we should take to fully charge the inductor? It's about 5 time constant. This is the time at least you should wait to fully charge your inductor, to increase the current up to its maximum value, to reach a steady value. Okay, so this is the RL circuit. The inductor, due to the nature of the coil of wire, it will like to oppose the change of magnetic flux And meanwhile, the magnetic flux is built by the current, so opposing the magnetic flux, opposing the change of magnetic flux correspond to opposing the change of the flow of current. So that is why once when you close the switch, it will not reach the maximum value immediately. Actually, at time equals 0, there's barely no current. At least you should take some time. So the time constant is for us to predict how long we should take to charge your inductor. And time constant means if you want to charge your inductor up to 63% of the maximum value, this is the time you should take. But this curve is asymptotically approach the value of E over R, but we cannot wait that long. We cannot leave that long actually. So if you want to charge your inductor, increase the value to the maximum value, the 5-time constant, about 5-time constant is the time that you should take. Okay, this is the RL circuit. I hope you like it. This is Nash.